Okay. Good afternoon, everyone. I'm going to talk to you about compressed sensing and the RIP, which is a common, very popular topic in lots of fields. So let's talk about compressed sensing. So let's suppose you have some kind of matrix or operator, and that might typically be an MRI scanner, for example. And you're given the output of the MRI scanner. And then you're trying to recover your original image X. So the MRI scanner takes in an image, and it outputs coefficients or something. And your aim is then to try and recover the original image. Now, if you want to do that, typically you need to get as many measurements as the length of your vector X. So if you want to recover 5 pieces of information, you need to take 5 measurements. That's a kind of fundamental barrier in linear algebra. You can't get more data, more information from less data. You can't really do that. But, I mean, while this is true in general, you can actually do some tricks here. And that's kind of the idea behind compressed sensing, a clever trick. So the point is here, we can break this barrier. And let's look at 2 examples. If we want to store the numbers 1, 2, 4, 2, 3, 3, 8, 5, we need to store 8 pieces of information, each of those numbers. But if we only want to store 0, 0, 0, 0, 0, and then a 1 in it, well, we need 2 pieces of information. We need to know where the 1 is and what number it is. And that's obviously some form of compression. And this is one of the ways modern computers compress images. So the point here is that we know loads of the values are 0. And we're using that little piece of information to store less. So in this case, we have 1 element, and everything else is 0. Now the point here is we call such a vector 1 sparse. If it has S elements which are non-zero, it's called an S-sparse vector. And we're going to exploit this idea of sparsity in order to break this barrier. And that's the general point of compressed sensing. So the problem is, if you know less measurements, you could have multiple possibilities for what your original image can be. But if you know, before starting, that your original image is going to have mostly zeros in it, then you can break this barrier. You can ask for the sparsest possible solution. And that's basically what's going on behind compressed sensing. There is a few more complications behind it, but that's the general idea. It works really well in practice. People are doing 15% of the MRI scans that they'd need to previously and getting pretty much the same results. Now, as a mathematician, you say, why is this natural phenomenon occurring? People are doing this thing in practice, and it is working, and we want to know why. What is the mathematical reason? So, the clever idea was this thing called the RIP, and I'll talk about that now. So basically, we were talking about S-sparse vectors being important, and a matrix or an operator or some kind of MRI scanner is said to satisfy the RIP if it behaves very nicely on S-sparse vectors. And this is the precise mathematical definition. But don't worry about it if you don't know what any of these terms mean. The point here is that you are nice on these S-sparse vectors. So if you're nice on these S-sparse vectors, if you can take an S-sparse vector and things don't change too much, then you satisfy the RIP. And if you satisfy the RIP, recovery is pretty much guaranteed for S-sparse vectors. So if you start with an image X and it's S-sparse and you ask to recover it, you can pretty much do it. If it's almost S-sparse, you're still fine. So if instead of zeros, it's 0.01, you'll just maybe lose that 0.01, but you'll get the rest of the information. And that's really useful. And it also works in the presence of noise. So MRI scanners are noisy, and you can deal with that particular problem. Okay, so this is the only gratuitous animation I have in this presentation. This is called the flip test. And the problem is it's really difficult to tell whether something satisfies the RIP. So what people have been doing is they've done these experiments, they've seen it works well, they write down, oh, we think it satisfies the RIP. Well, okay. There's a little test you can apply. Now, the test isn't perfect in the sense that you can pass the test and still not satisfy the RIP. But if you fail it, you definitely don't satisfy the RIP. And the way it works is this. So we take this vector here, where lighter values represent larger numbers. So this vector is pretty much S-sparse. and we try and recover it. So that would be what we'd roughly get when we recover. If the RIP holds, our recovery should be good. Now, if the matrix satisfies the RIP, what we could do is we could flip this vector around. So we start with our image, it has a lot of large coefficients at the beginning, and then it's mostly zeros. Then we flip it around. Then we try and recover it. If we satisfy the RIP, we should get something close to the original flipped coefficients. So we've got two different recoveries here. One of them, we just do standard compressed sensing. The other one, we flip, then we do compressed sensing. So that's the first recovery, just standard compressed sensing. And then the second recovery we flip, and that should be close to the flipped image, because we've done compressed sensing on it and we're expecting to have the RIP. And then we can flip back, and those two images should now be very similar to each other. So let's test it. See whether these matrices that people are using in practice do satisfy the RIP. Can I quickly finish this? Okay. So let's take an example. This is a crashed Ferrari, which is hopefully not how you consider my talk to have gone. So we'll do it. We do standard compressed sensing, and we get a result. And the result isn't perfect. I can't really demonstrate that it's not perfect, but it isn't perfect. But it's pretty close. When we flip, that's what we get. Utter nonsense. So clearly, this doesn't satisfy the RIP. And the problem here is that most of your coefficients are large at the beginning, and your matrices are good at capturing these beginning coefficients. So the RIP doesn't work, because the RIP is independent of ordering. So we need to be dealing with something which only allows us to capture coefficients at the beginning. Now, instead of talking about an S-sparse vector, where the sparsity is allowed to be anywhere, we talk about SM sparsity. And by choosing SM sparsity, where you're allowed to vary where the sparsity happens, this vector can be made sparse, and this one can fail to be sparse. And then you can define a new form of the RIP, called the RIP in levels, which is my concept. And a matrix satisfies the RIP in levels if it behaves nicely on SM sparse vectors. And what I've managed to prove is that if you have the RIP in levels, recovery is very good. Okay, so now some acknowledgements. I'd like to thank my supervisor for his obvious help with this particular problem and bringing it to my attention. I'd like to acknowledge my financial support from EPSRC, and I would like to thank Morio for the F1 image, which was very important for the talk. Thank you.
In your MRI example, what is actually sparse about the MRI image?
Yeah, so your original image isn't going to be sparse. So what you'll typically do is convert it into a wavelet coefficient. Now, when you convert everything into, I don't really want to go into too much detail for this because it's mathematically pretty intense. Right, exactly. So what you have is this basis called wavelets, and things are typically sparse in them. So you convert to wavelets, then you do your MRI. And the way people are doing this is also not ideal, but that will have to wait till the poster session.